That's the integral conductivity.
Okay. So thank you again for coming. The first speaker today is Peter Abbamonte, who will give an introductory talk about experimental techniques, and then after the break, present some of his own work.
Okay, so Blaise asked me to give an introduction to experimental science. He said there will be string theorists or holographers in the room, and I should make it basic. And he gave me 7 days or something to do this, so I finished about 6 minutes ago. He specifically asked me to talk about near equilibrium or weak probes, what I'm going to call gentle probes. This is a topic that's near to my heart. The reason is because the key advantage of gentle probes is they measure response functions that are intrinsic material properties that don't require you to understand every detail about the experiment. It's a timely issue, and the reason is in recent years there's been lots of efforts to build big facilities that can hit materials as hard as possible with bigger pulses of different kinds of beams and things. And I think the idea is if I hit my material harder, somehow more information will come out. What I'm going to argue is actually gentle probes are more precise. The aim being, the material is a very complicated many-body problem. You don't want an experimental probe that is another complicated many-body problem, because if you have to solve two many-body problems, it's a lot harder than just solving one. So what I'm going to do, and this is supposed to be a tutorial, Blaise asked me to do it, but he's not here. So, but I guess maybe he'll watch the YouTube video. So what I'm going to do is start by talking about just what are the relevant Green's functions in materials, just from a beginning standpoint. There's some experts in the room. I'm sure they'll correct me if I say anything wrong. And then I have curated a selection of experimental probes. There's an infinite number of probes out there. I have picked what I think, if you're, say, a young theorist, what are the 5 things that you need to know about? Of course, there's an expansive vacuum to explore of different probes. I think these are the most important ones. So they're EELS, infrared spectroscopy, neutron scattering, ARPAs, and STM. If you know those 5 things, you know 80% of experimental science. And there's 2 IR people in the room, one of whom is now smiling. Okay, so let's just start from the beginning. So let's suppose you have a solid and you want to understand it. It's an incredibly complicated many-body problem. So what do? If you go back in time and open Nosieras and Pines or some books from antiquity, they tell you that there's a set of essential Green's functions that you want to measure. There's an infinite number of Green's functions twos, not just 2-point functions, but 4-point functions and many other things. But these are the essential ones. And I just wrote them down. There's just the electron Green's function. Physically, what these things are expectation values of either commutators or anti-commutators. And I just saw my first typo. This should be an anti-commutator because those are fermion operators, not boson operators. This is just thermal expectation value. So the assumption is you have ergodicity and equipartition of energy and so on. And what these represent is the amplitude that if I put some disturbance at some location R2 at time T2, that it propagates to some other location R1 at some later time T1. So what G represents is I create an electron. I think I might have the daggers backwards. If I put an electron at R1 T1, what's the amplitude that it propagates to R2 T2? I think I have the order messed up. This is also supposed to be an anti-commutator. Sorry if it's a little presto. Anyway, but causality is critical. T1 is supposed to be later than T2. Whatever I do to the system now should only influence the state of the system in the future and not in the past. So that has important consequences for the analytic properties of these functions that I have on another slide. Anyway, so this is the basic one that governs quasi-particle propagation, just movement of electrons in a solid. There is a current response. So if J is an operator for the local current, then this tells me if I disturb the current at R2, what's the amplitude that current disturbance propagates to R1. This is a matrix because the current is a vector, so it has 3 components in the perturbation and in the measurement. So that's the second one. There's another one, which is the charge one, which is just disturbing the charge density at R2 and asking if how that propagates to R1. Critically, this is a component of this one, which I'll define in a second. So there's electrons, there's current, there's charge, and the last one is magnetism. So in the most general definition, this is a operator for the magnetic moment. It could have spin or orbital. Usually the spin term dominates, depends on the system. And again, this is also a 3x3 matrix because there's different components of the spin. So the reason these things are important is they tell you how things move in solids. They tell you how they respond to external fields, as I'll describe. And they also define what the quasi-particles are of a system. So a quasi-particle, by definition, is a pole in one of these things. In all of science, particles are poles in Green's functions. It's true in cosmology. It's true in condensed matter physics. Now, if you don't have good resonances, you may say there are no quasi-particles. These things can be incoherent. That's a property of the Green's functions too. So you can diagnose whether a system is a good Fermi liquid or not by the properties of these things. Okay, so I wrote down 4 things. There's really only 3 because the charge one is actually the same as the longitudinal part of the current one. So charge and current satisfy the continuity equation. And so the charge response is actually the longitudinal part of the current response. Longitudinal defines along the direction of Q. So if you know one, then you know the other. So the charge one is actually notoriously difficult to measure. We've been working on this in my group for a little over 10 years. And I'm going to argue this one's particularly important. By the way, I only have 14 slides, so don't hesitate to interrupt me, though they're a little bit dense. Okay, so typically we represent these things in Fourier space. Ooh, yeah, shoot.
Just going back, when you said that these were the longitudinal part of this is related.
Yeah.
Usually, so we have a conductivity. So the charge, the response function there, about current is related to a conductivity.
Yeah. I have a Kubo formula on the next slide.
But usually we think about that as something you measure with an optical response.
Yes, I have that
which
too.
is the transverse.
I have that on a slide coming
Okay.
up. Yeah. A whole slide on infrared. I didn't put transverse. Good. I'll come back to that point. I haven't talked about what a dielectric function is. So we'll get to that. Okay, so quick digression on, we rarely write these things in real space. It's much more common to write them in momentum space or frequency space. So we always Fourier transform them. And this is a recurring thorny issue in many fields. Because this if I just take one of these Green's functions, it's a function of 2 positions, R1 and R2, and then a time, T1, in principle, even 2 times, T1 and T2, though if the system has time translational invariance, it's only a function of the difference. If it doesn't have time translational invariance, that implies it is not a Markov system. And then it's another can of worms. So I'm just going to assume that we have time translational invariance. If it's periodic, then that's not, if you have a periodic driver, you can get Floquet bands and so on, and that's a whole topic. I'm just going to set that aside for the moment. Okay, so if you Fourier transform, then you have 3 Fourier transform variables, a Q1, a Q2, and an omega. So there are 3 things. So they're just spatial and temporal Fourier transforms. If the system is translationally invariant, then this chi will be a function only of the difference, R1 minus R2. Often that's the case, in which case this chi will only be non-zero if Q is equal to minus Q, Q1 is equal to minus Q. All the other ones will be 0. And we tend to call that chi of Q and omega. And I'll show you in a few minutes that when you do a scattering experiment or something, that's what you measure. So when you do a momentum resolved experiment, whether it's ARPES or neutron scattering or X-rays or EELs, you tend to think of the materials being homogeneous, but it's not really. What it is doing is measuring a sort of average over the response of the system. If it's periodic, then it's sort of an in-between situation. So chi is a function, but they always sum to a reciprocal lattice vector, whatever the Bravais lattice is that describes the periodicity of the system. So then most of them are 0. But there are a few that aren't. And then you have to specify what these G's are. Okay, so that's an important thing that's going to come up, especially when we talk about the relationship between ARPES and STM. And coming back to the point of causality, because you have these theta functions sitting here, that has consequences for the analytic properties of G. So what happens is these response functions always vanish at negative times. That's a choice that's made when you decided that you wanted to describe the system in terms of retarded responses. And that means the way that is accomplished is by assuring that all the poles in this quantity lie in the lower half of the complex plane. So that when at negative times, I have to close the contour vertically. When I Fourier transform, which makes the thing vanish, at positive times, I close it to the negative complex axis, and then I go around the poles. And I didn't have time to typeset them, so I put these out on my lecture notes. So the consequence of that is the real part and the imaginary part are related by what are called the Kramers-Kronig relations. So that's just a statement that this thing is causal. So I'm not sure students usually forget this. These Kramers-Kronig relations, which are in Jackson and most textbooks, these are 4 retarded Green's functions. It's a personal choice. If you wanted to describe the system in terms of advanced Green's functions, or in high energy physics, they often use time-ordered Green's functions, which play nicer with Lorentz invariance. These are not right, okay? So these are imposing retarded causality on the systems. Yeah.
But I mean, in terms of what you measure, it's not really a choice, right? If you actually do linear responses, the retarded functions that come out.
Not true. If you do a scattering experiment, you measure the imaginary part of this thing. You don't measure the real part. And you don't, and causality is a relationship between the real part and the imaginary part. And I have to put that in by hand. So when I compute this from that, there's a choice I get to make, which Green's function I want. I didn't prepare slides on that, but you might think, of course, the world we live in looks causal, right? But there's microscopically, there isn't a choice of, we just sort of perceive the flow of time to be the direction that entropy is rising, but microscopically doesn't mean anything. I have some papers on that we can dig into in the coffee break.
There's a question there.
Can I ask you a question on this?
Oh, yeah.
So
Sure.
pragmatically, how do you do this? Because you don't measure over infinite frequencies.
Ooh, good.
So what are the implications of cutting this off?
Excellent. Huge errors. It depends on how wide a range you go. Often, if there's a set of excitations that are of interest and you integrate over those, you can get a reasonably accurate measure of the real part from a measurement of the imaginary part, but there will be a constant offset that's unknown because there is spectral weight far away. If you cut it off near, there will be edge effects, and then it distorts the whole spectrum. And so then what people do is they extrapolate, but then the details depend on how you extrapolate. So if you try to apply these over a finite frequency range, it's a thorny thing. And Eric is an expert, and Peter too.
Can I make a comment about that? I mean,
Yeah.
it's not always, so also sometimes it's implicit. For instance, like we want to know the superfluid density in a superconductor, which is defined as the integral of the delta function.
Yeah.
We can't measure that. So we measure low frequency.
Yeah.
We measure a 1 over omega dependence
Right.
of the imaginary part.
Right.
And the coefficient comes from the integral.
Yeah. So
you measured one frequency there and your error is 0.
Yeah. Right.
Yeah.
So for that's the case. So there's many cases, many ad hoc cases where, so you sort of have to know what you're doing. Right. In X-rays, just as a plug for X-rays, which I'm not going to talk about unless you ask me, I can actually integrate over kilovolts, and then often you can actually get everything, and then it's quite accurate. So it sort of depends on the situation.
Peter?
Yeah.
Can I ask about a sentence on a previous slide?
Sure. This
So,
one?
Yeah.
Good.
If there are no, sorry, I was late. I would have asked earlier otherwise. So if there are no poles, there are no quasi-particles?
None that propagate these quantities. There could be some other quantity out there that propagates this long.
Say that I take the Boltzmann equation,
Yeah.
0 temperature.
Yeah.
I turn off all collisions.
Okay.
I have quasi-particles, right?
Yeah.
Yet, when I compute these Green's functions, there are no poles, there are only branch cuts.
Really?
Yeah.
Okay. Well, is there another Green's function that has a pole in it?
The single particle Green's function,
This one.
the one where you don't integrate over the whole Fermi surface.
Yeah, that's this. So then
Yeah.
that has a pole in it. So that's would be, then these guys wouldn't have poles, and that would tell you that those are the relevant quasiparticles. So these are the fermions. Let's say if it's an electronic system.
So as you know,
Yeah.
as you know that I like.
Well,
the
you
way
and
I
I.
say this is that, you know, the quasi-particles, you don't see them as poles in many body retarded Green's functions. You only see them as poles in the electron Green's
Yeah,
function.
this is the electron Green's function.
Yeah, but not in the many body ones. In the many body ones, the poles are not quasi-particles.
Okay, I mean, this is a many body quantity. These are all many body eigenstates.
Sorry, but to go to a different case then, I mean, can you have a pole in the current and not have a pole anywhere else? If you have a pole in the current, wouldn't that be a
Yeah, actually,
particle of
Blaise,
some sort?
Blaise, you and I have a paper on strontium ruthenate.
Yes.
It has a pole in this thing,
Yes.
but not that one.
Hence, that pole is not a quasi-particle.
But how do you define a quasi-particle?
Okay,
Is that a charged
Good.
electron?
That's actually why I put this on here. There's different communities define quasi-particle differently. Some people, and I thought Blaise was one of them until now, any of these things with the pole would be a quasi-particle. If you go to the March meeting in the United States, most people mean a quasi-particle is a pole in this one specifically. Poles in the other ones you call collective modes. It's terminology.
I would tend to agree with what you just said, but
Yeah.
discussing with people, they seem to tell me that any pole in any retarded Green's function is a quasi-particle.
I don't know who they is. If they is me, then that's correct. But if you go talk to Andrei Chubukov, you'll get, it's a different they. He'll tell you these are not quasi-particles. That's that one. So it depends on who you talk to. Good. This is really going great because I don't have that many slides, so I needed some questions. Okay, so a few details. Most of the time when we make measurements, we measure some Hermitian quantity, like the density, and Hermitian quantities are real. And the consequences, these susceptibilities will be real. The one electron Green's function is an example where this is not true because a wave function is not an observable. Anyway, but if it's density or current or spin, then these things are all real. So the consequence of that is that the complex conjugate of this thing, which is it's complex thing, so it has a complex conjugate, is actually related to chi star of q and omega is chi of q and minus omega. So it's a symmetry that's present. It's entirely a consequence of the fact that, say, the electron density is real. In addition, if the system has inversion symmetry, then the response at q will be equal to the response at minus q. So chi of q and omega will be chi of q and minus omega. Okay, and that has a simplifying effect on the Kramers-Kronig relations, because the real part of chi will then be even in frequency and the imaginary part will be odd. So if you actually open up Jackson and ask what are the Kramers-Kronig relations, they actually look like this. They're written as the integral from 0 to infinity with factors of 2 out front because they've assumed a symmetry. But there are two assumptions hiding in that. The first one is that there's a Hermitian operator inside the definition of the Green's function. And the second is that the system has inversion symmetry. If you have a ferroelectric, these are not right. Oh, well, they do in this slide. I don't get these from these unless I can relate minus omega to positive.
Usually
omega.
that would follow that reduced form of them on the right there follows from the fact that in the time domain, which they come from a Fourier transform of, it's a real quantity.
That's what I wrote here.
Yeah.
And inversion symmetry. Otherwise, this negative omega is related to the negative q. I need inversion symmetry to write these. The q here are the same as the q there. This is why I wrote this down.
Yeah.
Okay. Two of these Green's functions, in my opinion, are more important than all the others. The first one is the density response. And the reason is it's related to so many different quantities, as Peter alluded to a minute ago. So the density response chi, I'm just going to call it chi here. It describes how the system, how charge responds to perturbations in the charge. And that means it sort of contains information about screening. So it describes how the system moves charge to react to charge that's been placed into the system. So chi is actually related to the dielectric function, the longitudinal part of the dielectric function. It's actually a 3x3 matrix, but this relates to components along Q. V of Q here is just the Coulomb interaction. It's just 4 pi e squared over Q squared in Gaussian units. So V chi is dimensionless, and this is epsilon. So it tells you how the system screens. It's also related to another quantity called the polarizability. So everybody has a different name for the polarizability. Some people call it chi-naught. Some people call it the irreducible bubble. I always call it capital pi out of Federer and Welechka because I like to make it, it's a very different thing than lowercase chi. And what this tells you is how the polarization evolves from the total field E. So this is like, this thing here is chi E if you open a textbook on E and M. So pi is the polarizability, V is the Coulomb interaction. So this tells you if I put the system in an electric field, how does it polarize? It's related to screening, but slightly different effect. And chi has some basic properties. Some of the most important ones are its sum rules. So if I take chi and I take the imaginary part of chi and I multiply by omega and I integrate over all frequency. And again, Eric, there's an issue of infinity, what that means. It just sums to the density. So this is a very important relationship in optics because often you measure this thing, but you don't know it in absolute units. It's in photons per second or electrons per second. And if you want to calibrate this thing, then you can do it if you know the density and you can measure to infinity, whatever that means.
Should this be Q or E?
Q. I'm sorry, what? There's Q
Those
here.
are two different Qs. One is the charge and the other one is momentum.
Oh,
Yeah, that's what I thought.
The one on the right is charge. It's Q squared, it's E squared.
this is momentum, Q.
Oh, here's
This N has the E in it. This is
So if I
charge
set Q to
density.
0, then I get 0.
Yeah, chi Q, the imaginary pair of chi Q equals 0, 0. And the reason is chi is a measurement of how electron hole excitations modulate the density. If I have a system and I don't have any way of modulating the Q equals 0 density by creating electron hole pairs, right?
Yeah.
So the limiting property, that's conservation of charge is this statement. Question at the back.
Yeah, sorry, you're assuming anything about the relation of energy and momentum here, or?
It's Galilean invariance is
Galilean
hidden in
invariance,
this.
oh.
Yeah.
All right, thanks.
If you don't have that, there's another version of it, but I don't know what it is off the top of my head. As Peter alluded to earlier, there is a relationship between chi and sigma. Sigma is the conductivity. So this thing is related to the longitudinal conductivity. And good. So chi is also related to this pi. And pi satisfies what's called the compressibility sum rule, which is if I take the zero frequency part of this polarization and the limits don't commute, so it's important omega goes to 0 first and then Q. Take the Q equals 0 limit. This is the density squared times the compressibility of the system. This is a quite extraordinary thing because if you measure, say, the plasmon in aluminum, apply this sum rule, and then apply the compressibility, you actually get the correct compressibility for aluminum this way. I find it quite a remarkable thing that I can do a measurement of an excitation at 15 eV and deduce what the static compressibility of the system is. So it's another sum rule that's important. The last one is somewhat obscure and it's called the Friedel sum rule. And it basically it says that, so basically it uses the fact that chi tells you how charge propagates. So if I put some external charge into the system and I multiply by V chi, then I get the induced charge. And so if you Fourier transform this, then you get a convolution integral. If I assume that the external charge is just a static point charge, Q, then in a metal, the induced charge should be exactly minus Q. That's the definition of a metal. A metal is a thing that screens charge completely. The consequence of that is in the long wavelength limit, V chi has to be -1. Okay, so that is the definition of a conductor. And in aluminum, this also works.
Can you explain again, or can you explain why the F sum rule is a consequence of Galilean invariance? Because I would say what Galilean
physically-
invariance tells me is that whatever's on the right hand side
Yeah,
is in fact n over m.
yeah.
But I would think that Galilean invariance has nothing to do with telling me that on the right hand side I have some quantity times q squared. that
I don't have a
quantity has to
profound
be
answer.
the weight.
If you open Nosieres and Pines, they assume that the Hamiltonian is p squared over 2m plus a whole bunch of many body terms that they don't know.
Okay, so
And
that
the p squared is what gives you this q squared.
fine.
So that's,
I would say then that what Galilean invariance constrains is the fact that that precise ratio is n over 2m.
okay, yeah, it could be,
What you need for the thermal to exist in the first place is translation invariance,
yeah. Oh,
which is independent of any assumption on Galilean or any type of boost symmetry.
I think to have Galilean invariance, you have to have translation invariance.
No,
Because otherwise there's no, then the.
no, these are two independent generators which commute.
Okay, the derivation of this assumes translational invariance.
Yes, I think that's the fundamental
also
thing.
true, yeah. Great. Oh, yeah,
So this confuses me. The Kubo formula here for the conductivity.
Yeah.
So this is just a conservation equation, right?
Yeah.
But this chi, is this the chi that would show the plasmon or not? And in that case, would that also then show up in the conductivity? Is that really the case? I thought it would be pi there instead of chi. Or maybe I'm mixing
I
up.
think you might be right.
It should be
So,
pi,
I
right?
think it's
And
pi.
then I've seen some papers that actually
That's the longitudinal conductivity.
Oh, it's
so
longitude, okay, yeah.
This is right.
Yeah, actually,
right,
yeah,
right.
okay,
The longitude,
right.
but if you have the transverse conductivity, it should rather be pi or something?
The transverse one isn't related to any of these because these are all longitudinal quantities.
But aren't they?
Well, then there's a transverse conductivity related to the transverse susceptibility, which I think in your units is, or in your notation is v pi.
You can take the
Yeah.
limit, you can take the limit q to 0.
This pi is still the longitudinal one.
Take the limit q to 0 in the conductivity.
Yeah,
You have to
then
be
they
very
should-
careful with it. but
Well,
yeah.
this goes to 0 like q squared.
yeah, so
that's
then
why you
And
can
so
take the
this
limit on both
thing in
sides.
q equals 0 is well defined. It's just a number.
Yeah, so then you get the optical conductivity and everything checks out. Okay, fine, good.
Okay, so this is one of the important Green's functions. The other really important one is the one Blaise was discussing, which is the electron Green's function, G. I don't know what important means. Important means if you go to the March meeting and ask how many talks discuss the quantity and make a histogram, this is usually the one at the top. So again, this thing just tells you how this should be anti-commutators. It's a fermion quantity, not a boson quantity, so it's a typo. Describes how electrons propagate in the system. If it has a poles, that means they're long-lived quasi-particles that are electron-like. If it's incoherent, then there aren't. If you Fourier transform this thing, again, there's the issue. It has two momenta, K1 and K2. If the system is homogeneous, then it's only non-zero if these two Ks are the same, and then this is G of K and omega. Very important, if you write it out in terms of the many body states of the system, it looks like this. So it has some matrix elements. This is an annihilation operator. And the exact form depends on whether you're talking about the electrons or the holes. So there's a plus side and a minus side of the Fermi surface. This psi n are many body eigenstates of the n particle system. And this psi n plus 1 or n minus 1 are many body eigenstates of the n plus 1 or n minus 1 electron system. And this is either a creation or annihilation operator. So basically, in Fourier space, you can write it directly in terms of the eigenstates of interest. You can see that if I take this to be an annihilation operator, I take my n electron system, remove one electron, I ask how that overlaps with the n minus 1 electron system missing that electron. The reason I bring this up is because photoemission measures this exact thing, which is my next slide. And then you get resonances when these denominator vanishes. So a very important quantity is the imaginary part of this thing, where this denominator just turns into peaks, and that's called the one electron spectral function. So this is one of the most important quantities in a many body system, is this A. In a Fermi liquid, it looks like this. This is in all the textbooks on many body theory. So this is energy, that's the Fermi energy there. And then as a function of K, if you have some band passing through the Fermi energy, you'll typically see a resonance. The width of the resonance will go like E squared, where E is the distance from the Fermi energy. So the lifetime will diverge as you approach the Fermi energy. And then it'll have some shake-off processes that are related to whatever the collective modes are in the system, phonons or plasmons or whatever. So this is normally when people plot band structures in solids using photoemission, which I'm going to talk about in a minute. They typically show pictures that look like this. But a very interesting set of systems such as strange metals. This resonance doesn't really behave right. It doesn't have an energy that goes like E squared. It'll just be linear in E. And then you have sort of marginal Fermi liquid stuff going on that we're going to start talking about today in my next talk, because I have to give 2 talks.
It's an imaginary part of G. Yeah, right.
Oops. You know, it's so stupid. I'm going to fix it right now. Probably. Good. Thank you, Conrad. All right, so let's talk about experiments. Ooh, yes.
Can we see the zero sound collective mode in this figure?
No, because that's a boson.
I see. Okay.
But I guess, so then,
If it's coupled to the quasi-particles, what were we going to say? That?
no.
Oh. Well, let me answer the question. If the quasi-particle is dressed by the zero sound mode, then you'll see it appear as a satellite in the photoemission spectrum. I haven't told you what photoemission is yet.
I see.
But the best way to measure it is with eels. What were you going to say?
Confused about K's and Q's on the slide.
By tradition, G is always written as a function of K, and Q, the bosonic functions are written as a function of Q.
So
Because Q is typically K1 minus K2, because it's made of electron hole pairs. It's just a tradition.
But there should be a Q based on the previous slide, which is the Fourier transformer space.
Yeah.
And then there should be a K. Which
These were supposed to be Ks. I can call them K or Q.
but then there should be also a K or a P that labels the Fermi surface. And
Yes.
these are 2 distinct things.
These are the labels of the Fermi surface. That's why they're typically called K, because this is measuring the fermion quasi-particles.
So to comment on Han's question, zero sound is a dispersion relation in Q.
Q.
The
Zero
Fourier transform
sound.
through space.
Zero sound shows up
in
in
here because
Right.
it's not a linear mode in the Fermi wave number.
Zero sound is a pole in this thing.
Yeah.
And this thing is obtained from that other thing by integrating over the Fermi surface.
You would need to get chi from A or G, you would have to do a theory where you made electron hole pairs and do a convolution, and then you'd have to put in vertex corrections and Coulomb interaction. It's a mess. That's why we can measure both.
So it's not easy to directly see from this measurement.
From no. ARPAS is for measuring the fermion.
Okay.
Or in other words, this is showing you single particle poles, so quasi-particles.
Okay.
And zero sound is a collective mode, so you're not going to see it in this one.
Right.
Okay.
Yep. Okay. I'm not having problems going too fast. So I'm just going to talk about the probes that I discussed. So we're going to start with eels. So this is electron energy loss spectroscopy. It's basically inelastic electron scattering. It's called eels for historical reasons. I don't know where the name came from. But I think this is, so I just wrote a review article on this with Jörg Fink. And it sort of lays out the arithmetic for all the other probes. So I only have to do it once. So basically scattering is done using time-dependent perturbation theory in the interaction picture. So you start with some initial state, which is a many-body state of the electron system with a probe electron in it. And then the final state is another one with the final electron. And then the way one gets scattering is by calculating a time evolution operator in an S matrix. The matrix scattering matrix element is this. So H prime is the interaction, whatever that is. So you see interaction picture, you separate out the unperturbed Hamiltonian from the perturbed one. And then H prime is just Coulomb interaction. So it just says the probe electron interacts with all the other electrons through Coulomb. So if you write this thing out, it's just a matrix element of rho of Q. That's the momentum density operator. And then this is V of Q and some constants, that's M. And this is Enrico Fermi, 1930 something. So the scattering cross section is 1 over the flux times the transition rate times the density of final states, and you can put a Bose factor or a Boltzmann factor in there if there's finite temperature. So the transition rate is just 2 pi h bar times the matrix element squared. The density of final states for electrons goes like root E. So it's just electrons in a box. If you put all that together, you see something wonderful, which typifies all weak probes. The cross section is some numbers that are just units basically, times a quantity called S of Q and omega, which is the density correlation function of the system. So there's this function in real space and time, it's called S of R and T, that's typically called the Van Hove function. And it's how the density at R prime T prime correlates with that some other distance away integrated. So it's just a 2-point correlation function for the density. So you can write that out in terms of the many body states, and it looks like that. So here's the critical thing about weak probes. This is just a property of the system. I don't need to know anything about electron scattering or any kind of spectroscopy to make a theory of S. That's a property of the material. So this is why weak probes are so important, because they're simple. You can relate them to intrinsic material properties, and they're even the ones in the textbooks. I should contrast this with, no, I'm not going to do it because this is going to go on YouTube. But if I blast the system really hard, then the response that I get isn't just a property of the material anymore. It'll depend on the properties of the thing that I blasted it with. And then I have a many-body problem that's related to my probe that I have to solve before I can understand something about my material. Now, if I have a simple material piece of silicon and I blast it with my probe, whatever that might be, I can learn something really interesting because I have a simple material and a complicated probe, and I can learn about an interesting many-body problem, which is the coupling between the two. But if I have a complicated probe and a complicated system like a strange metal, it's really hard to make progress. So if you just look at the probes that have contributed to progress in condensed matter physics over the decades, they're the 5+ X-ray scattering that I wrote on the first slide. So if you're a young person just getting started, I would focus on these things and move on to the more difficult ones in time. Okay, so S is called the Van Hove function. It's just a correlation function. How it's related to Green's functions is given by the fluctuation dissipation theorem. So this S is just proportional to the imaginary part of this cut. And I don't know what the real part is. It depends on what causality I pick. And that's a whole topic. Because if I take the retarded Green's function or the advanced one or the time ordered one, and I Fourier transform them and I take the imaginary part, they all look the same. The causality isn't in this statement anywhere. So this is what you get. Critically, S is actually a function of 2 different momenta, not just one. So when I do this measurement, though I only have one momentum transfer, what I'm actually measuring is the diagonal parts of this thing. Okay, so it's sort of like some average response if the system is heterogeneous, but it would be the exact one if I have translational invariance. And so in other words, the imaginary part of chi I get is this, and there's a minus here, but not there, which is in this paper that I wrote a long time ago. EELS basically tells you what are the charge collective modes. For example, if you wanted to measure zero sound, this is the thing to do.
So the question, what is the estimate of the size of relativistic corrections?
To this, I have no idea. Never. I'm a condensed matter person. I only did relativity in my class. Though I know some nuclear physicists who work at JLab, and they're also doing EELS. And everything is Lorentz invariant in their equations. And I've always wondered if it matters. You and I should discuss that this week.
What are you asking, Conrad? Well, I mean, you make I don't have any question, but you make the non-relativistic approximation for the Coulomb exchange.
Yeah. And everything assumes an instantaneous Coulomb interaction.
But if you have small sample sizes, it's very natural, right? Roughly speaking, the photon will never interact, will only interact once. So you make this approximation. You know, to have either appreciable distances that the photon can interact more, or other way of saying it, if the energies are such that, yeah.
You know, we see things like that because often you don't just see one excitation, you see harmonics because the thing scattered more than once. And we usually, in that situation, we usually say the experiment didn't work.
But it's about whether the photon scatters more than once rather than
The electron.
The electron.
Yeah,
Electron can
okay.
scatter many times. That's not an issue.
I mean, it is, we usually ignore that. All this is single scattering, by the way. Okay, I only have 10 minutes, so. All right, there are two IR experts in the room at least, but here's my Wikipedia version of infrared spectroscopy. This is also an incredibly important probe. It's typically done using a Michelson interferometer and an FTIR setup. There are a bunch of different schemes for doing it using ellipsometry and so on. But basically you start with a source, you put a beam splitter and have a couple of mirrors, and then you either measure the reflectance or the transmittance through the sample. And then this is broadband, and then as you scan one mirror, what you do is you measure different Fourier components of the optical response of the system, either the reflectance or the transmittance. So the reflectance is a complex quantity. It has an amplitude and a phase, and if you rewrite the Kramers-Kronig relations, you can actually relate the amplitude and phase to one another. It's just a re-expression of the same Kramers-Kronig, so it ends up being the log of R and theta. So if you measure, so the point being, I can measure the amplitude of this thing, and if I do it over a wide enough range of frequencies, which is what this was designed to do, I can deduce the phase through Kramers-Kronig, modulo the edge effects that you referenced before. So that gives me everything. I get the real and imaginary part of the index of refraction. If you're interested in optics, those are what you want. But typically what one wants is the complex dielectric function, epsilon of omega. So you might say, why should I do this if I have EELS? Because EELS measures this thing as a function of Q and omega. There's two reasons. The first one is this has exceptionally high energy resolution, sub-milli eV. So it's a reference, and it's you get epsilon in absolute units as long as Kramers-Kronig works. So it's a very important reference point. Also, the Q equals 0 properties of materials are sort of the starting point. If you don't know that, you don't normally proceed to momentum-dependent measurements until this thing is already done. So it's really the comparison of the two that's important. Yeah, so very high resolution, Q equals 0 only, but that's an important limit to understand. So this is infrared. What's next? All right, neutrons.
It's okay, you have until 11.
I have till 11. I just have one slide on each probe. Neutron scattering is a fantastic technique. It's typically done at a reactor. The big one in Europe is called ILL, it's in Grenoble. But there are spallation sources like Rutherford Appleton Lab in the UK and so on. But generically, you start with a reactor, and then it sends out a broadband beam of cold neutrons, and then you have to monochromatize them, which is typically done by reflecting them off a piece of graphite. They usually use graphite monochrometers. And then there's a sample, which it scatters from. And then there's an analyzer, which is another graphite monochrometer. So this is called a triple axis spectrometer. The axes are 1, 2, 3. This is invented by Bertram Brockhouse, Chalk River Labs in Toronto. If you're ever in northern Ontario, it's not in Toronto. If you're in Toronto and you just drive north and just keep on going, eventually you get to Chalk River Labs. There's a Nobel Prize 1955 for this. So all the arithmetic is the same as for EELS. The only difference is the interaction. The neutron interacts with the magnetic moment. There's also a cross-section for the nuclei. So neutrons are great for measuring phonons. This audience is probably more interested in the spin excitations. But anyway, so what you measure is another Van Hove function, not in terms of the density, but in terms of the magnetic moment. This thing is a tensor because m is a vector, and it's just a 2-point correlator for the magnetization. So this thing is, and that shouldn't have been a G, this should have been S of R and T. At any rate, you can Fourier transform this thing. So that's the neutron Van Hove function. So there is a fluctuation dissipation theorem for this quantity, S alpha beta, which is the imaginary part of chi. That's the magnetic Green's function I showed you earlier. And that's literally just chi m. So if you take the Q equals 0, omega equals 0 limit of this thing, that's just the magnetic susceptibility. If you take a piece of iron and put it in a squid, go near a phase transition, the magnetic susceptibility that's diverging, it's the Q equals 0 limit of this. So absolutely basic fundamental quantity. And so what do you actually measure? So if you actually write out the cross section, the relationship between the measurement and this chi. There's an interesting little quirk, which is neutrons actually measure only the transverse part. So this is the full matrix S. Of course, what you measure is neutrons per second in the detector. And that's because you sum over the transverse components of this. And if you use polarized neutrons, you can actually separate out some of the different components this way. Yeah.
So this is still belonging to your like gentle.
This is gentle. Neutrons is the most gentle probe there is.
Right.
A neutron can pass through 10 centimeters of aluminum and not interact once. Right. So that's actually the issue. So you normally need samples this big hockey puck sized samples. Anybody know Bernhard Keimer? No?
Yes.
He's a legend in Europe. He discovered the magnetic resonance mode in high temperature superconductors because he was the first one who had YBCO crystals like hockey puck sized. So you could take them to the reactor and measure the thing. My favorite neutron paper is a paper by Bella Lake on potassium copper fluoride, which is just a nice 1D spin 1/2 chain. And that's a system that you can solve with beta ansatz. So in this paper, 2013, on the left-hand side is the neutron scattering cross-section. This is energy, this is wave vector. You can see there's some spin waves. If you solve it exactly in beta ansatz, you get the curve on the right. So neutrons just work. Okay. Finally, the most important one, ARPAs. So, Peter, are you awake? Okay, because I might need some help with this one. Okay, so photoemission is, I think it's probably the most important probe in condensed matter physics in terms of like every material you find, the first thing you do on it is ARPAs. I mean, the first thing you do is measure the resistivity and see if it's a metal or an insulator, but after that you do ARPAs to see what the bands are. ARPAs is the photoelectric effect. So Einstein, 1905, you shine light on a sample and electrons come out. It's not a scattering technique, it's an absorption technique. So there's no differential scattering cross-section to talk about. Nevertheless, there is a transition rate that is relevant. And basically there's an interaction Hamiltonian, there's a initial state and a final state. And the interaction Hamiltonian is the interaction between light and matter. So it's not Coulomb now, it's A dot P. Okay, and then these many body states have particular properties when the electron is ejected from the sample. So when you pull the electron out, it goes into a plane wave state. And that means that this n particle final state is the n-1 system in the presence of a plane wave with wave vector k, electron plane wave. Similar for the initial state. So this matrix element actually factors. It factors into a thing that's just a property of that plane wave, which we call the matrix elements. And then then an overlap between the initial n-1 body system and the final one. And the final one, yeah. So if you write this out, the intensity, it's that overlap function times some matrix element squared and then energy conserving delta functions. This is the analog of Fermi's golden rule for photoelectrons. And the key thing is if I look at the initial state of this n-1 system, what it is the n electron ground state, many body ground state with an annihilation operator on it. So take the many body system, remove an electron, and then I'm left with an n-1 many body state, but that's not an eigenstate of the system. What it is, it's a representation of the overlap between the ground state and the ground state with one electron missing. So it tells me in a many body sense how a hole propagates in the system or what state that electron was in before it left. Okay, so that thing is, if you write out this quantity, it is literally the imaginary part of this one electron spectral function that we wrote down earlier with a C operator in it. Now, this can either be C dagger or C, depending upon whether you're measuring above the Fermi energy or below. Photoemission only measures the occupied state, so this is just an annihilation operator. At any rate, the intensity in a photoemission experiment, if everything's working and there's a whole bunch of caveats of the sudden approximation and so on, is the incident intensity and some matrix elements times a Fermi function if it's at finite temperature times A of k omega, which is the one electron spectral function. This measures exactly what the many body overlap on an electron is in the ground state of the system. It's incredibly important. If you have a simple band system like silicon, you'll see nice dispersing bands. You can map out band structure with this. If you have a strange metal, you just get an incoherent mess and it's a topic. So what this does is really important. The only caveats here is it's a surface technique. So you only measure the electrons at the top layer. And again, only measures below the Fermi energy. Measuring above the Fermi energy is something that we need to be able to do. Nobody does that.
You can.
Well,
You can invert the process.
It is. So inverse photoemission, which traditionally is called Bremsstrahlung isochromat spectroscopy, because I was Sawatsky's postdoc, so I learned all about it, exists. So this is where you shoot an electron beam at a sample and you measure the light coming out. And then you have to change the angle of the electron beam or something. And it's really hard. The yield is really low.
What's the advantage?
You measure the unoccupied states. What's going on above the Fermi energy, we just don't know. Somebody needs to do this.
Peter,
Some of these quenched time-resolved ARPAs are just above the Fermi level.
Well, okay, time resolved. What they do is they hit it with a laser, and then you excite a bunch of electrons above the Fermi energy. And now there's some holes, and then you see some stuff. And what that stuff is the unoccupied states in the presence of a bunch of now holes in the occupied states that are interacting with them. So if interactions are completely irrelevant, you can see some vestiges of the unoccupied band structure. So usually the effective masses are wrong because it's renormalized by interaction with all these holes. It's a way to get a little glimpse of what's going on. Actually, what works better is just heat the sample up. So the Fermi energy's kind of got a tail. That works too. Heat it to 1,000 degrees. If it's a many-body system, it doesn't work.
sorry, Peter, can I just ask you, with the development of your reflection yield system, would that be a nice way to do inverse photo emission?
No.
Why not? What is
Because of the electron hole interaction in most things just dominates. For example, if we measure an insulator, and this is true for you, actually, if you were giving this talk, I'd ask you that, and you give the answer that I'm about to give you, which is if I say I measure an insulator, I cannot measure the band gap that way. What you see are the exciton lines, because electrons and holes interact. So and even when you don't have bound states, they're excitonic effects, they're shift spectra weight around. You never really know what the spectral function was on the other side of the Fermi energy. We just don't know. The message is if there are any budding experimentalists in the room, a great career would be inverse photoemission. Somebody could get it to work. It'd be the only game in town. We're almost done.
Sorry.
Yeah.
This equation, I equals I naught FA.
Yeah.
Yeah. Can you say again where you measure, where you know, and you want to extract A, right?
You want to extract A. I is the matrix elements and the intensity of the beam and stuff. So you know the beam intensity.
This I know. This is a quantity that I fully know.
This is usually mostly known. Yeah. There's matrix elements in here that depend on because this is a dipole operator. So it depends on the exact wave function geometry. But typically this isn't strongly energy dependent. So I can sort of normalize it out. The frequency dependence all comes from this. And so if
this is what you extract.
You normally extract that.
Yeah.
Yeah.
But what are nu and A bold?
Nu, forget what nu is.
So nu is just the photon energy that you're using to extract.
Nu is photon energy. Yeah.
And
H
A
nu
is
photon.
A is polarization of that photon beam.
Yeah.
So it can be linear, horizontally polarized, or circular, and that will change the matrix elements that appear in your interaction. Sorry, where are they? The phi.
It's this
there,
thing here.
yes. So depending on the polarization you choose there, you'll get different overlaps.
So this will determine how well you couple to a particular mode, but the energy and momentum of the mode will all come from this A. So this is typically considered just a constant out front. It depends on geometry. Yeah.
And it's largely unknown.
What's that?
It's largely unknown and not understood.
It's often known.
I would argue not.
Okay. I'm trying to make Blaise think we know what we're doing. Last slide. Last slide is STM. I did this at breakfast, and these equations literally came off the Wikipedia page. So I bring this up because it is a critical comparison for photomission. Okay, so how does STM work? You take a tip, typically a tungsten tip. This was invented in IBM Zurich in the 70s. You can do it by taking a crystal and cleaving it along certain facets, but it's possible to make a tip that's literally atomic, has one atom sitting at the bottom. Then you put that thing on some piezo stages, some PZT with some voltages, and you can bring it near a surface. So then if you smash it into the surface, that's a technique called point contact spectroscopy, which is a whole genre of measurements. But the idea here is you leave a little gap, and then the vacuum in between acts like a tunnel barrier. The electrons can tunnel across this gap. So if you calculate what the tunneling current is, it depends on Fermi functions now, because the Fermi function of the sample and of the tip. So there's a sample which has some electronic structure. There's a tip that has some electronic structure, and what you're measuring is the convolution of these two things. So the difference between them is the bias, and then the amount of current you get depends on how many states there are displaced due to the difference in bias. So at zero temperature, so there's some matrix elements here, and those are quite complicated. They're simpler than they are in photomission, but what they are is exponential in the distance between the tip and the surface. So they're very, very strongly geometry dependent. But if you sit at fixed distance and just scan the voltage, that thing is roughly constant. And then the intensity will just be, assuming you're at zero temperature, so that these are just step functions, then you just get a convolution of the tip and the sample. And now there's an assumption, and this really is a matter of finding a good tip. Typically people use tungsten. Tungsten, the density of states is roughly constant in energy, roughly. I'm told by STM people. I'm not sure I believe it, but at least they're all using the same tip, so we can compare one system to another. At any rate, if the tip is constant, then the sample density of states is just the derivative of I with respect to V. Now, here's a crucial thing, and I couldn't find a good reference on this, so you're just gonna have to take my word for it. Density of states is an independent electron concept. Okay, so that only means something if you have infinite square well and you start putting electrons in it and ignoring the interactions. What actually happens if I throw an electron in or pull an electron out is I'm measuring a spectral function. So what STM measures is the same spectral function measured with photomission. So this dI/dV is minus 1 over pi times the imaginary part of G, which is the same, it's related to the spectral function measured in ARPES. And I bring this up because there is a constant point of confusion, because this is a real space measurement. That tip goes down to a particular spot on the surface. And remember, if the system, G is actually a function of two positions or two momenta. In photomission, you measure the diagonals in momentum. In STM, you measure the diagonals in real space. So this measures A of R and omega. Photomission measures A of K and omega, but they are not Fourier transforms of one another. They are diagonal terms of two big matrices that are Fourier transforms of one another. So you can't just Fourier transform ARPES data and get STM data, though they're very closely related. There's a whole field called quasi-particle interference, where you put sort of the right amount of disorder on the surface and you look at how, so the quasi-particles scatter gently from it. And it's another gentle probe, if you like. And then you can do a model and you can relate the electron hole excitations measured in photomission to an interference pattern seen in STM. You can actually measure quasi-particle dispersions that way if you have the right kind of disorder. But of course, if you have no disorder, it doesn't work. Because if there's no disorder, the system's translationally invariant, and I get the same spectral function every point in the sample. If I Fourier transform it, I only see weight at the gamma point. There's nothing anywhere else. So it's a very important point of comparison for photomission. And it can measure the unoccupied states, because I can send electrons in or electrons out. So it's a way of getting a glimpse of the unoccupied quasi-particle dispersions in situations where that works.
I'm confused again.
Yeah. Okay, shoot.
The previous slide, we're talking about Ks, which are momenta on the Fermi surface.
Exactly.
On the next slide, R is real space.
Correct.
If I would Fourier transform that,
yes,
I'd get the Fourier transform of real R.
K, yeah.
And that's nothing to do with where I am on the Fermi surface.
It absolutely is, yeah. I'll give you an example. Let's suppose you take a piece of gold and you decorate some atoms on it.
Yeah.
Those will scatter, and I'll see interference patterns around them in an STM. Those are called Friedel oscillations. They're screening of the electron gas, and they have wiggles. The period of those wiggles is KF, or 2KF. And if you take those wiggles and you Fourier transform, you can actually see the Fermi surface of gold. This was done by Ward Plummer in the early 90s. So it's K, not Q, that is in this A.
Wait, hang on, Peter, I'm not sure I agree with that.
I'm not sure I agree there.
Because, I mean, that works because in that particular example, you have a spherical Fermi surface.
Yeah, right.
But in the cuprates,
It's much more complicated.
and in topological insulators, you actually measure Q. You measure
Yeah, right.
you measure the
Well,
connection between
yeah.
2 points on the Fermi surface.
It's a valid point.
And you need a model to work out what the actual Fermi surface is.
Well, and the Q enters because the electron is scattering off the impurity, and that's the momentum transfer is there. Yes, it's K initial, K final of the electron. Of course, this is still measuring a fermionic function, but how it varies in real space depends on how those fermions scatter and Q enters. He's right. I didn't have time to make a slide on it. The point being, relating this to ARPAs is possible, but takes some work. You can't just Fourier transform. Pretty much done. Any questions? Yeah.
So how does transport fit into this picture? And in particular,
Yeah.
let's take the optical connectivity. Why don't I just drive an AC current through the material and measure the AC current? Or I mean, maybe just measure it. Is that not
As
gentle?
opposed to doing what?
Optical IR for,
You can't get to high frequency, but if you could, you would.
all right.
So
Yeah,
yeah, there's
because it's
the max, the fastest power supply out there can oscillate at hundreds of gigahertz. If I want to go a higher frequency than that, so a terahertz is 4 milli eV.
Yeah.
So it's ordered. So if you want to start looking at plasmons, you need to go faster. But actually, the line between transport and optics becomes blurry when you get to the gigahertz. So people who do microwave spectroscopy, they talk using language of transport, but they're actually measuring reflectivities of waves and stuff. So you can deform continuously from transport to infrared, just by changing the frequency.
Peter, will you discuss optics more next week?
Yeah, more to come.
I've heard sometimes like with the eels, right, in the Q0 limit, like that's different than ER optics, like the Q0 limit. Like, is that now the same or?
They're the same.
Same?
Yeah, you can relate them. So yeah, we have papers where you take the Q equals 0, the smallest momentum you can reach in an EELS measurement, and you can take the IR data and they overlap. So it's really measured. Now infrared, good. Actually, infrared typically measures the transverse part of the conductivity. So this epsilon is a matrix, 3 by 3. So when I reflect light off of a sample, the E field is transverse. So I actually measure the transverse parts of this thing, not the longitudinal one. Now, in the Q equals 0 limit, in most cases, the transverse and longitudinal response are the same because there's no distinction when Q is really 0. But there are cases where those two limits don't commute and the transverse and longitudinal response are different, like some superconductors in finite systems that can happen.
Okay.
So people tend to get lazy because of when they commute in like boring metals, and then we just leave indices off of these things which I shouldn't have done. But maybe Peter will fix this when he gives his talk coming up.
You also measure imaginary part of 1 over epsilon.
Yeah.
So that's another important part, right? So
right.
Like in some, you could imagine an optics experiment where you were sensitive to the imaginary part of epsilon. But in his EELS, he measures the imaginary part of 1 over epsilon, not the 1 over the imaginary part of epsilon.
Right.
So these are different.
Yeah. So
things are related.
Things are related, but the reason you have different probes is they measure slightly different things. But if you compare them and they agree, then you feel happy, you know what you're doing. I didn't even talk about X-rays, but I'm not gonna. We can discuss it at the coffee break because I think I'm out of time. So, we're done. Okay. Thank you.